Okay, hi everyone. Okay, so I will start. Okay, those who are joining, yeah, please join. But this one I will not continue from the beginning. Yeah, so later, okay, when I put this together, okay, I will combine the two videos and then we'll give you the full version. Okay, so for this one, okay, I am going to straight away, okay, go over here, okay, which is going to be. Okay, the question that we are going to start is going to be question 3. Yeah, question 3C. Okay, so here, okay, we have this equation representing standard electropotential, yeah, for the reduction of this compound. And then, okay, in the acid solution that is given. So the E value is 1.92 over there. Okay, so now, okay, they want you to draw a diagram, okay, for the apparatus that we will use to measure the E value. So when you are measuring the E value, the apparatus, yeah, so we need to first, okay, think about the half cell, yeah, for the half cell setup for the hydrogen cell. So you can see the delivery, okay, for the hydrogen gas, and you can see platinum electrode, you label accordingly. The electrolyte is going to be H plus 1 mole per dm cube, and you will have the salt bridge voltmeter, okay, and then to measure the E value. And then you have, okay, for this one, you see there is going to be ion and ion. Okay, so the moment you see ion, and we can also see the H plus. So ion and ion, yeah, we have to use the electrode as the platinum. So you can see platinum. And then the electrolyte, we use the H plus. Okay, we use MnO4 minus and Mn2 plus, all in 1 mole per dm cube. So you are going to have that, okay, and this is going to be the apparatus that we will use to measure the E value. So you draw accordingly. Now, the next question is, okay, use the data booklet to identify a substance that could be used to oxidize Mn2 plus ions to MnO4 minus ion. Okay, so we want, okay, to oxidize this structure. Yeah, so let's actually look at the entire oxidation number first. Okay, so if you look at the oxidation number over here, this is +2. Yeah, the oxidation number of this you can count, which is going to be calculate, which is x plus -8 equals to -1, x equals to -1 plus 8, it's going to be +7. So you can see that they want you to oxidize. Yeah, if they want you to oxidize, it means in this case +2 to go to +7. Okay, so we want this particular equation to go to the left. So if you want this equation to go to the left, okay, what you need to do is you must join with another E cell, which is going to be greater than 1.52. Yeah, so if you get that E cell, okay, the standard reduction potential, which is greater than 1.52, then that equation is going to, that half equation is going to go to the right. Okay, so you go and look at the data booklet, and I have actually looked at the data booklet and found out that, okay, I've selected this. Okay, maybe you just go through and see which one is suitable. Okay, but I have found out that this is going to be 2.01. Yeah, and I'm selecting this. Yeah, so you see 2.01 is greater or more positive than 1.52. And I know that this is going to go forward and this is going to go backward. Okay, so when it goes backward, okay, so in this case, I already changed it. Yeah, I have, hold on, yeah, I have changed, okay, this equation to the backwards reaction. Okay, let me check. Okay, so you see here, okay, Mn2 plus, okay, 4H2O. So I put it over here. So therefore, okay, this one is going to be 1.52. Now it's going to become -1.52. And now I'm going to cancel the electrons. So we know that 2 electron and then 5 electrons. So I need to times by 5 times by 2, everything. Yeah. So when you join all of them together, this is going to be the equation that you will get. Okay. And okay, write the equation. This is the equation, and the E value. Okay, why, under what basis I selected this? Because I want, okay, something that has more, okay, more positive than 1.52 volt over there. Yeah, the E value, so that, okay, it is possible to oxidize, okay, the Mn2 plus to become MnO4 minus. Yeah, this is important. So 2 marks done. Yeah. So if I move forward, number 4, okay, give the mathematical expression for each of the terms. Yeah, for this one, if you want to give the mathematical expression, quite simple. Just, yeah, pH is going to be negative log H plus, and then Kw, yeah, for Kw, okay, don't go and include the water, because water, we know water, liquid, okay, they are going to give you H plus and then OH minus 1 mole and 1 mole. So when we write the Kw is H plus, okay, and then OH minus, and then we are not going to divide with the H2O because H2O is going to be liquid. So Kw, we just use this. Yeah, so I just use this. Yeah, H plus, concentration of H plus times with the concentration of OH minus. Yeah, now calculate the pH of NaOH. Now, since we have the Kw, okay, we know that, okay, if you have pure water, okay, the Kw is going to be Kw 1 times 10 negative 14. You can check from the data booklet. Yeah, so this one everyone should know. Okay, you can use the Kw, okay, in this manner. Okay, if you have this Kw 1 times 10 negative 14, the H plus I need to find. Okay, but the OH, okay, we assume, okay, we assume the OH from the water itself is too little. We assume all the OH is actually coming from the sodium hydroxide, because sodium hydroxide, when they dissolve, they give you 1 mole of Na plus and 1 mole of OH minus. So if you are using 0.027, so you have 0.027 over there. So you can calculate what is going to be the H plus, the concentration, and you will get this concentration. After that, you can calculate the pH. Okay, you calculate the pH and you will get 12.4. There is another way to do this, okay, which is going to be, you can calculate POH, okay. pH is negative log H plus. POH is going to be negative log concentration of OH minus, which is going to be negative log, okay, 0.027. Okay, and when you calculate, you will get, okay, that value. Okay, if you calculate, let me quickly calculate for you. Okay, if you calculate that, okay, log 0.027, you will get 1.57. Yeah, POH. And do remember, because of the Kw, yeah, pH, okay, plus POH equals to 14. This one is still related to this, okay, this Kw. So in this case, if I want to find out what is my pH, pH is 14 minus 1.57, which is you're going to still get, okay, 12.4. Yeah, this you need to yeah, basically you just calculate and you will get this 12.4. Yeah, now 3 significant figures. Okay, now the Ka value of chloric acid, this is going to be weak acid. The moment you deal with weak acid, okay, you just know in our syllabus we have this formula, Ka equals to concentration of H plus to the power of 2, then divided by Ha, concentration of Ha. Ha is going to be your weak acid. Yeah, so you just need to calculate the pH. So you need to find out the concentration of H plus first. Yeah, so I put all these values, H plus to the power of 2, concentration of the weak acid is given, so you just put over there. Find out, okay, Ka we know, okay, find out what is the concentration of H plus. Once you find out the concentration of H plus, this is the concentration of H plus. Okay, I use the formula for the pH. pH is going to be negative log concentration of H plus, and you will get pH after you calculate, you get 4.71. Okay, quite simple, quite straightforward. Okay, but in order to do this, okay, you need to memorize the formula. Okay, that's why this is very important. You need to memorize. Okay, so if you don't memorize, okay, you are going to be struggling to find out how to do this. Okay, of course, you can do it by deriving. Okay, but since it's going to be 2 hours paper, I don't think so you'll have enough time, yeah, to derive and so on. Okay, let's move forward. Okay, water and octane 1-ol forms 2 layers when mixed. Okay, so ethanamide, okay, is more soluble in water compared to octane 1-ol. Yeah, so it means basically they are soluble in both. Okay, when 1 gram of ethanamide is added, okay, to water, then shaken with 50 cm cube of octane 1-ol. Okay, they found out that the water layer contains 0.935 gram. Okay, so what I can do is find out, in water layer you have 0.935 gram. So of course, what happened in the octan 1-ol? So I can find out 1 gram minus 0.935, and I have this gram. Okay, so if I want to find out what is going to be partition coefficient, so you need to define. Okay, so I defined it as this: ethanamide in water divided by concentration of ethanamide in octan 1-ol. Okay, when I do that, of course, this is, we count from the gram. Okay, you need to change into mole, and then you find it in terms of concentration. Okay, so here I put 0.935 divided by MR, but I don't put the MR value. I just put first, and then 50 divided by 1000, 50 cm cube, change it into dm cube, and then you have 0.065, which is going to be in octan 1-ol, divided by MR, and then divided by 50 divided by 1000, still 50 cm cube. So from here, I can cancel, so you no need to find out the value. You can cancel this. MR is the same, ethanamide, MR. You cancel and you cancel. In the end, you are going to get this value. Straight away, mass divided by mass. Doesn't matter the MR and the volume. Then you will get the KPC, which is going to be 14.4. So as they mentioned that ethanamide is more soluble in water because we use in water, of course, it's going to be greater than 1. So you can see 14.4. So that is going to be the answer for this. And the trick over here, if sometimes students will ask, how about if it is, how do we know is ethanamide in octan 1-ol divided by ethanamide in water, or like what I did over here? So in this case, you just straight away look from the question itself. They say ethanamide in water and octan 1-ol. So water comes first divided by octan 1-ol. So you can use it as a way to give you an indication what divided by what. So that is important. Now, this one, is going to be slightly tricky. Do not actually straight away go into this question thinking it's so easy and just do, because first you are dealing with different volume. You cannot simply cancel. You are dealing with different volume, and you are taking 0.935 ethanamide, then shake it with pure octan 1-ol. You know what the student will do? Most of the time, they just use the 14.4, the same thing that you found, and then, you just put 0.935 and then divide by X. You forget one thing, because, this is the amount, of ethanamide in water. And certain portion from here will go and dissolve, in octan 1-ol. And let's take that amount, in mass, which is going to be in gram, as X. So I need to put minus X, It means that, KPC at equilibrium, you see the ethanamide in water at equilibrium is 0.935 minus X. Very important. And divided by the volume. Don't simply take the volume, because now we cannot simply cancel, So it's 50 cm cube, change it into dm cube, 50 divided by 1000, so it's going to be 0.05. And I am going to use the X, which is going to be the mass in the ethanamide in octan 1-ol, divided by 0.1. Why? Because they say it's 100 cm cube. So change it into dm cube, 0.1 divided by 1000. Once you do that, you are going to have equals to 14.4. You just need to go and look for the X. This one using your maths. Figure out how to calculate. You calculate. Once you calculate, you will get the value is going to be 0.114 gram. Where is the mistake that students will always make? This one. They will ignore this X. They will use 0.935 only. That is wrong. Another mistake is, they forget, must divide by this, must divide by this. Sometimes they go and add, 150. Do remember, this 100 cm cube of octan 1-ol and 50 cm cube of water, they don't mix. So you no need to add them. Yeah, but in certain cases, in normal calculation, we add and to find the final concentration. But in this case, they are immiscible liquids. Okay, so you do not need to add. Yeah, they are just going to be 50 cm cube and then 100 cm cube separately. Yeah, so you cannot simply cancel also. Yeah, so please take note. Okay, but do remember this one. I'm taking into the assumption that I am dividing this, okay, with the same MR, okay, and then I cancel divide by MR, divide by MR, okay, so I cancel the MR. Okay, do remember if you are wondering about why suddenly I'm just using the mass alone, because the MR you can cancel. Okay, you can cancel. Okay, I will get the answer as 0.114. Okay, I leave it in 3 significant figures over there. Now, the next question, which is going to be question number 5. This one is going to be a bit confusing. Yeah, maybe a bit difficult. Okay, because okay, you need to do certain assumptions. Yeah, so you see a solution is made, yeah, by dissolving this, okay, copper sulfate in excess aqueous ammonia. Yeah, this solution, okay, contains copper complex, okay, with the 4 molecules of ammonia. Okay, so we are going to write the expression of stability constant, yeah, K step. Yeah, so what you do, okay, when you go and put in excess aqueous ammonia, aqueous ammonia contains water. Yeah, so if you have copper sulfate 5H2O. Yeah, this is the assumption. Maybe some students, most of you don't know this. Yeah, this one take note. Yeah, when you have this copper sulfate, yeah, with 5H2O, okay, when you put them in excess aqueous solution, yeah, before it reacts with ammonia, before ligand exchange actually take place, yeah, they are going to form, okay, this when they add this H2O, okay, they are going to have 6 ligands of water, okay, will be surrounding the copper. Yeah, so I will remove, okay, if sulfate, you see the sulfate, okay, will come out, okay, because it's 2 minus, and you can say that this sulfate is going to be like something like what we call as spectator ion. Yeah, spectator ion. So whatever it is, yeah, when you add with excess aqueous ammonia, yeah, this is going to be changed into this. This is very important. Yeah, they are going to change, okay, from here to here. Very important. Now, once you have that, okay, then, okay, they will react, okay, with ammonia. So you can see like what they want the reaction to happen. It will react, okay, where the 4 ammonia molecules, okay, will do the ligand exchange, okay, with the water. They will remove the water. Yeah, you are going to get this, and you are going to get all these are going to be 0 charge. Copper was 2 plus. Yeah, so it will still be 2 plus, and then they remove 6 water, so 6 moles of water, okay, will be there. Okay, so you can actually let's actually also look at the marking key also. Okay, hold on. All right, I will keep the marking key also here. Yeah, so they want us to find out what is going to be the K step. Yeah, the K step, okay, is going to be, we will ignore the water. Yeah, water is liquid. Yeah, it's constant concentration, so we don't want that. Okay, so I will have, okay, this, okay, molecule. So I have this molecule, and then divided by this. Okay, you see this. Okay, if you don't change to this, you will not get this. Please remember that. And then ammonia to the power of 4. Yeah, because I have 4 over there. Okay, so that is what they want in the marking key also. Yeah, please take note of this. Okay, now after you write the stability constant, okay, state the color of the solution. This solution, yeah, copper with ammonia, this is going to be a deep blue solution. Yeah, you can check from your notes. Yeah, it's going to form a deep blue solution. Now, then, yeah, we have this copper. Okay, this deep blue solution is heated gently. Yeah, and they will remove the ammonia. Yeah, you remove the ammonia. Some of the ammonia remains in the solution, and some forms ammonia gas. Yeah, the color of the solution changes. Yeah, a precipitate of CuOH2 is forming, and then you are going to collect. Okay, so they say a sample of this, okay, added to concentrated hydrochloric acid, then you have reaction forming a copper complex Y. This is also going to be concentrated hydrochloric acid means there's going to be a ligand exchange, okay, will happen. So they will form the, I think if you memorize this, it's quite easy to memorize, okay, you are going to get this ligand, okay, which is yellow color, yeah. So a sample of this copper hydroxide also, okay, is added to dilute sulfuric acid, okay, a reaction also takes place, and you get another complex which is going to be Z. Okay, so we are going to, they also mentioned that, okay, all these three complexes are different color. Okay, let's actually look into one by one. Okay, suggest an equation, okay, for this, okay, to form CuOH as the aqueous solution. Okay, so what will happen? Okay, so they mention, yeah, when this one is heated gently, okay, then ammonia is being released. Okay, so when you heat gently, when ammonia is released, what is actually happening? You need to write down first, okay, this one heated gently, you are going to have copper 2 plus, okay, with ammonia, all the ammonia, or they say some of it stay there, yeah, you have copper 2 plus, okay. Now this copper 2 plus, okay, after that they say, okay, they are going to be, you are going to suggest an equation to form CuOH as the aqueous solution is heated. So what happens, okay, you are going to form CuOH2. Okay, in order to form CuOH2, okay, what you need to have, okay, because here I have ammonia, yeah, of course I need to have something over here that will give me the OH, yeah, so that one will come from water, yeah, so I just put include water over here, okay, and I am going to get, okay, like what they mentioned, they are going to give you CuOH2 form, yeah, so I put CuOH2. Why I have included water? Because I want to form this, okay, and what will happen in that process? Ammonia is going to be released. I put ammonia going to be released over there. And if I use the OH, you see water, okay, I use HOH, HOH. And I am using 2 OH over here. So this one already used up. So left with what? This 2H plus. So this is going to remain 2H plus. Yeah. So this is the first equation. Okay, when you are going to have this copper with ammonia heated gently, okay, you remove the ammonia, and then, okay, you have this precipitate, so you have this precipitate and so on. So this one is solid. If you want to write down also the state, you can write down aqueous, this is going to be gas, this is going to be liquid, yeah, so this one is going to be they mention it's going to be solution, yeah, so solution is aqueous. Okay, now suggest an equation for the reaction with this with concentrated hydrochloric acid. This one I told you they are going to form this. Okay, so you just need to write, okay, a ligand exchange. Okay, you are going to react with the 4H HCl, and then you see the 4Cl will come in. So CuCl4. Okay, Cu is already 2 plus, and then Cl is negative 1, so you have 4, so negative 4, so plus 2 minus 4, you get 2 minus. And then what will happen next? Okay, you have OH, OH, and then 4H plus, so 1H, 1H, okay, 2 moles of water. Okay, so what will happen to the remaining 2H plus? They will stay. Okay, so this is going to be how to write the equation. Okay, now next question, okay, complete the table with the color and the geometry. So you see the first one, the Y, yeah, Y we know, okay, is going to be CuCl4, this one, yeah, CuCl4 to minus, okay, so CuCl4 to minus, okay, the color of the complex is going to be yellow. Yeah, and this is going to be a tetrahedral structure. Yeah, and then the Z, yeah, you can see the Z, okay, is going to be the reaction take place forming a colored copper complex, which is going to be Z. Okay, what actually taking place? Okay, you have the copper hydroxide with H2SO4. Okay, what happens generally is going to be reacting with water first. Yeah, when they react water, okay, the Cu2 plus, okay, they are going to be combined with 6 ligands of water. Yeah, this one is quite common. So if you have, okay, previously you have this one, Y is going to be yellow, okay, different color, okay, Z must be different color, and this one is going to be, just now they mentioned that they are deep blue solution, so Z must be different color also. Cannot just see, it is a complex. I cannot say copper sulfate, yeah, copper plus sulfate, copper sulfate. No, it's not complex. So you need to come up with a complex. The complex that we are going to talk is CuH2O6 and then remain as 2 plus, and this is going to be the pale blue solution, or you can say blue solution. And you can see 6 coordination numbers, so it's going to be octahedral. You can write down this. Yeah, so this is going to be maybe slightly difficult, maybe something that is not always what we do, yeah, but it's going to be something that you need to also learn. Yeah, now the next part is going to be explain, okay, why the complexes X and Y and Z are colored and why the colors are different. So Y and Z, yeah, they are going to be attached by different ligands. Yeah, so you need to mention the d orbitals, okay, of the complex. They split into 2 non-degenerate d orbitals. 2 non-degenerate d orbitals means they have different energy level, so they have different energy gap because of different ligand. Okay, and different wavelength or frequency of light, okay, is going to be absorbed when the electron from the lower energy level is promoted, okay, to the higher energy level. So they are going to absorb different energy. So you are going to see a complementary color, yeah, based on the color that is being absorbed. Okay, but do remember, okay, because of a new syllabus, okay, depends on what type of complex. In this case, they didn't specify. Okay, if let's say if I look at Y, okay, I know Y is going to be tetrahedral. Okay, okay, but Z is going to be an octahedral. Okay, if you have, okay, like Y, okay, is going to be tetrahedral. This is being added in your new syllabus. Z is going to be octahedral. Please remember the orbital splitting are going to be happening in a different way also. Yeah. So according to your syllabus, octahedral, okay, when we draw, is going to be up and down side over here. Okay, so you can remember up and down 2. Yeah. So what I do is there are 2, okay, 2d. There are 2d orbitals, okay, 2d orbitals, okay, at a higher energy, okay, and then d orbitals, you have 5 d orbitals, yeah, so you have 3 d orbitals at lower energy. Okay, this is important, newly added in your syllabus. For tetrahedral, okay, you are going to have different. You will have 3d orbitals, okay, 3d orbitals, okay, which is going to be at higher energy, and the 2d orbitals will be at the lower energy. And the 2d orbitals that they are talking about, yeah, so you need to also know what is the orbital. Okay, these are going to be the dz square and d x square y square. Okay, these are the 2, okay, d orbitals, okay, that are going to be slightly different. So please actually go through this, okay, because in March paper, okay, paper 42 March 2021, they did ask question on this. Okay, so we are expecting this to come out also, yeah, in your paper, okay, in 2022. So let's actually move on further. Okay, question number 6. Okay, when you have, okay, this 1 mole per dm cube of this added into a solution containing Ag plus, a linear complex is being formed. So they already mentioned you are going to form a linear complex. Okay, so if you have that, okay, so you know Ag plus, how it can form linear complex. So it cannot just simply form a linear complex with only one ligand, right? So they are in order to form linear complex, you have to have 180 degrees. So you must actually have 2 coordinate bonding, yeah, with 2 ligands. And you see that they mentioned that S2O3 2 minus, they are a monodentate ligands. So there will be 2 okay, S2O3, okay, 2 minus, okay, S2O3 2 minus. Okay, so define the term monodentate ligand is a species, okay, that can donate one lone pair of electron, okay, to form one dative bond to the central metal atom or metal ion. This is very important, okay, dative bond, one dative bond, okay, and give the formula of P, including the charge, okay, this one is quite important also. Just now I told you, 180 degrees, okay, so you see, must have two ligands. If not, you are not going to get a linear complex, okay, so you will have Ag, okay, and S2O3, okay, then you put 2, okay, you see 2. Don't go and put like this, Ag plus, okay, S2O3 2 minus, or this one must times 2, then you have Ag2, Ag2S2O3. No, we are not talking about that. Yeah, for ligand formation, it doesn't work that way. Yeah, so please take note of that. It doesn't work that way. Okay, so this one is going to be Ag, okay, S2O3, because we follow the geometry. Yeah, they say that there are two dative bonds being formed. Yeah, so once you have that, you need to count the charge. This is going to be +1. Okay, +1, you have -2, -2. What is the overall charge? Okay, so you add all of them. Okay, so the overall charge is going to be +1. Okay, and then -4. Okay, you get -3. So you need to show the charge -3. Yeah, so that is going to be the formula of P. Yeah, now the next question is going to be when you have 1 mole per dm cube NaCN, okay, and then you add to solution P, yeah, which is going to be this one. Okay, a mixture which includes a second linear complex, yeah, is being formed. So second linear complex, quite simple. So you have Ag plus, okay, you put Cn. Cn is obviously the another ligand. So you must have Cn here, another Cn over there. I think quite simple. Okay, so in this mixture, okay, they found out, okay, that concentration of Q, which is going to be the one that with the Cn, yeah, the one with the Cn is more. Okay, so when something is more, okay, when you talk about ligand exchange, we are talking about stability constant. Okay, it means that the stability constant, if it is going to be more higher, yeah, so they are going to prefer to form with that ligand. Yeah, so in this case, okay, they ask you, okay, first write down the equation. So I just write down, yeah, the previous stuff. I add with the 2Cn. How do I know it's 2Cn? Yeah, because it's linear. They already mentioned. Okay, so I just put over there, and I will have this. Okay, what is the charge? So you see Ag plus Cn is -1, so you have 2 negative. So +1 minus 2 is -1. So that's why it's -1. And then 2 molecules of this will be released. So you can also check the total charges. -3 over here, then -2 over here. Total charge -5. Okay, so here you see -1. Okay, -1, then 2 minus and 2, so -4 you times, and you will get -5. Left and right, the charges must be the same, so they are the same. So this is going to be valid. Yeah, now suggest a reason why the concentration of Q is much more greater than concentration of P. Okay, so Q, okay, which is with the Cn, is more stable. Yeah, so they prefer to form this compared to the one that with S2O3. So it means that the ligand, okay, Cn ligand is a better ligand, but we don't say that. Yeah, we just say that, okay, the complex, which is the Q complex, is more stable. Yeah, why it is more stable? Because the K step, okay, the stability constant, okay, to form Q is higher than the K step of P. Yeah, so if it is higher, it means the position of the equilibrium is going to be going to the right for forming Q, yeah, in comparison to forming P. Yeah, so you include that will give you 1 mark. Now name the type of reaction in which P forms Q. So it means there is going to be this ligand is going to be exchanged with the Cn. So this is going to be a ligand exchange. Okay, but if you look at the marking key also, they also include some other term. Okay, you can use ligand exchange, which I suggest you to use. Okay, but if you want to write down displacement, ligand substitution, yes, go ahead. But do remember, okay, last time also we learned about this. Okay, if let's say it is forming a precipitate, then the name should be precipitation reaction. If it is forming salt and water, then the name should be acid-base reaction. Yeah, but only when you don't have any other thing, like in this case, there's no other thing that you can use. So then only you use the term ligand exchange. Yeah, please take note of that. Okay, the next part is going to be, you have this platinum. Okay, platinum forms a complex ion with the following formula. So you see, this is the coordination number is going to be 4. Yeah, the moment you see coordination number 4, they can exist in form of tetrahedral, they can exist in form of square planar. So two things, yeah. But the moment you see Cn, normally Cn, okay, they tend to follow square planar, yeah. Unless we are talking about CuCl4, okay, then 2 minus, then they will always follow. They will always follow tetrahedral. Okay, if you follow NiCN4, okay, then they are going to be. This is going to follow square planar. Yeah, please take note of this. Yeah, so it depends. Okay, Cn is bigger, so they prefer to use the square planar. Okay, so similar with platinum. Okay, because there is Cn, okay, they are going to form, okay, square planar, not tetrahedral. Just take note of this. So in this complex, okay, the carbon atom, okay, they are going to have the Cn, okay, to bond with the platinum. The complex shows stereoisomer. We have two types of stereoisomerism, okay, which is going to be the geometrical isomerism, which is going to be cis and trans, and the another one is going to be the optical isomerism. Okay, so in this case, there are only two isomers of this complex. Okay, because they have the Cn, so I put the Cn because I know it's going to be square planar. Okay, so I put the Cn over here, Cn over here. Okay, and then Cl and Cl. You can see Cl and Cl and Cn and Cn, they are side by side. So therefore, this is a cis isomerism. Yeah, and another isomer that I can draw is going to be, I put the Cl and Cl over here, Cn and Cn opposite to each other. Yeah, and that is going to be your trans isomer. So when they say describe the geometry, no problem, square planar. Yeah, and the type of stereoisomerism, you can write down geometrical isomerism. Okay, and if you want to be specific, cis and trans isomerism. Okay, but no optical isomerism. Remember that, yeah. In order to have optical isomerism, yeah, there is going to be, maybe you need to make sure that all the 4 groups are different. Okay, but when it comes to transition metal, I think the one that we are going to look at, maybe if you have bidentate ligand, 3 bidentate ligand, and so on, yeah, then we can have the octahedral structure. Then they can have the optical isomer and so on. For this one, no, yeah, only going to be cis and trans. Okay, so I will move forward. Now, question number 7. Okay, they say that phenol is a weak acid. Yes, correct. Phenol is a weak acid. Phenol can be made from phenylamine. Okay, give the region and condition for this reaction. So if you have phenylamine, okay, phenylamine, this is going to be benzene, and then you have NH2. Okay, so you are going to make, okay, phenol. So if you want to make phenol, do remember, okay, if you have phenylamine, you need to change it into benzene diazonium salt first. Yeah. So what you need to do, you need to make sure you have NaNO2 and HCl. Okay. And then you put them, you react them, and you are going to get HNO2. And then you are going to get NaCl. Okay, so this is going to be prepared at 5 degrees Celsius, less than 10 degrees Celsius. Okay, because if you use a higher temperature, they are going to decompose to give you N2, yeah, nitrogen gas. We don't want that. Okay, once you do that, okay, you are going to get this benzene diazonium salt. Yeah, so it means the reaction. How do we get this? Okay, so this phenylamine, okay, if I just write in terms of equations, C6H5 and H2, okay, when I react with HNO2 and HCl, I am going to get, okay, this C6H5N2 and then Cl, yeah, and then what should I do, yeah, with this benzene diazonium salt? I need to warm that with water. Okay, when you warm that with water, you are going to get phenol. Okay, this is how you get, okay, phenol. Okay, so give region and condition for this reaction. Okay, you need NaNO2. Okay, you need concentrated HCl. You need 5 degrees Celsius. Okay, so after you do that, you are going to get C6H5, okay, N2 plus Cl minus. So after that, okay, what you need to do, you need to warm, okay, with water. Okay, so when you warm with water, it will change into phenol. Okay, so benzene diazonium, okay, this salt will change into phenol. So please take note of that. Yeah. Now, phenol reacts with dilute aqueous nitric acid, okay, under room condition. Do remember phenol, the OH group. Yeah, the OH group is going to be very quite interesting, because OH is an electron donating group. So when they donate the electron, okay, they are going to make the electron density of the benzene ring to become higher. So when the electron density is quite high, yeah, the electrophile, they are attracted. Yeah, they are attracted to react, okay, with the benzene ring. So therefore, okay, if you have normal reaction where you need to use catalyst, yeah, you need to heat up and so on, okay, for phenol, you don't need to do that, because, okay, the electron density is going to be more, so it makes the reaction much more readily available. Yeah, readily available. So here they say when you react with aqueous dilute nitric acid, because normally, okay, you need to react with concentrated nitric acid with the catalyst H2SO4, concentrated H2SO4 with 55 degrees Celsius to get nitrobenzene. Yeah, so NO2 into that. But now if you have phenol, okay, you do not need to have all these conditions. Okay, you just need to have dilute aqueous nitric acid, okay, room condition, room temperature, and so on. You will get, okay, and you can see here, okay, they mention C6H5NO3. Okay, what does it mean? Okay, I know that. Okay, I know the first one, it has phenol. Okay, so I know C6H4. Why H4? I know that the NO2 will come to another, it will replace the H. Yeah, so one of the H will go off. Okay, so the NO2 will come in. So when I try to count, yeah, when I just put them together, okay, I have C6H5 and O3, which is going to be matching with whatever that I have over here. So what it is going to tell me, yeah, I know that only one NO2 is going in. So no need to worry about two, yeah, no need to worry about all, yeah. So only one NO2. But where do I put them? Yeah, do remember, okay, OH is going to be electron donating group. So they are going to activate position 2, 4, 6, okay. 2, 4, 6 will be activated. Okay, so here you can see position 2. This is going to be position 4. This is position 6, but position 6 in this case is the same as position number 2. Okay, so we are not going to put 6 nitrophenol over there. So when you name them, yeah, so it's going to be 2 nitrophenol, phenol, and nitro NO2 is at position number 2. And if you name this is going to be 4 nitrophenol. Yeah. Now, next, okay, you have phenol reacts with excess aqueous bromine. Now, normally when you react, okay, with bromine, yeah, you need to have halogen carrier. Okay, so in this case, if you react with phenol, no need halogen carrier. Okay, and if you have excess, all the positions, okay, will be substituted. What kind of position? Okay, because OH is going to be electron donating group, they will substitute at position 2, 4, 6. Yeah, so 2, 4, 6. Okay, the Br will go in. Okay, and you are going to get 2, 4, 6 tribromophenol. Yeah, so that's going to be the name. Yeah, the next part, describe 2 visual observation. This is very popular. Yeah, when you have, okay, 2,4,6 tribromophenol, please remember this is a white crystalline solid. Yeah, white solid. Okay, so white precipitate is going to be formed. Okay, and then the second observation is going to be, since you are reacting with Br2, is a brown solution. The brown solution is going to be decolorized. Yeah, because there is reaction. Okay, so that is going to be the 2 visual observation that we will see. Yeah, write an equation for the neutralization, okay, in which phenol behave as an acid. Yeah, phenol C6H5OH. Neutralization, first thing that should come in your mind, sodium hydroxide. Yeah, so sodium hydroxide with the acid, yeah, weak acid, what will it give you? You will get salt, C6H5O minus Na plus, O minus Na plus, left with what? H2O, so salt and water. So you just put salt and water over there, done. Yeah, and then you have water, phenol, and ethanol can all behave as acid. Okay, so we are going to look at it in form of a different order of acidity. So if you look at this phenol, okay, OH, okay, and then if you look at C2H5OH, okay, when they give you, yeah, phenol, okay, C6H5OH, they are going to give you H5O minus and H plus. Okay, water will be still later we will compare. Okay, and then we have C2H5OH. Okay, they are going to be, all of them are weak acids, so they will give you C2H5O minus and H plus. Now, when you look at it, yeah, so this one, okay, the O minus, okay, the electron, the lone pair of electrons, okay, that you exist in your phenoxide ion, okay, what it will do, okay, they are going to go and delocalize in the benzene ring. Yeah, so they are going to be delocalized in the benzene ring, making it, yeah, making this charge to become less negative. Yeah, so it is going to stabilize. Okay, you can say stabilize, okay, the phenoxide ion. Okay, so this movement, yeah, the delocalization of electron, okay, the delocalization of electron into the benzene ring. Okay, you can write in full. Okay, delocalization of lone pair of electron from the O minus phenoxide ion into the benzene ring. They stabilize the phenoxide ion, okay, making this reaction to be formed more. Yeah, so it's going to be forming more because it's more stable. In that process, you are going to get more H plus. Okay, but it is going to be different when you look at the ethanol because they are going to form ethoxide ion. So this ethoxide ion, what is the difference? They have this R group. This is the R group. R group is going to be the alkyl group. Yeah, so this alkyl group is going to be electron donating group. Yeah, so you just need to say the alkyl group is electron donating. Yeah, so they are going to be acting as a positive. They will give you the positive inductive effect. So what is positive inductive effect? Yeah, they are going to push the electron, yeah, towards the oxygen over here. And what they will do, okay, because they are pushing the electron, okay, this is going to make this electron over here, the charge, to become more negative. So when it's more negative, negative and positive, they like to form reaction. So they are going to form more. They will react and form C2H5OH. The position of the equilibrium will be shifted to the left, yeah, because of the positive inductive effect. Because of that, okay, they are going to be less H plus. So making it less acidic, yeah. So the most acidic is this, less acidic is this. The one in the middle is going to be water. So you need to explain. Okay, so in 3 marks, okay, where the explanation will go, okay, you need to actually mention, yeah, you see, the lone pair of oxygen is delocalized into the benzene ring. Okay, done. Okay, this one will give you 1 mark. This one will give you 1 mark. For ethanol, positive inductive effect of the alkyl, yeah, so, or the ethyl group. So you mentioned about that. And then you say about stability of the phenoxide ion, yeah, so this is going to be more stable, so it will weaken the bond. If you want to say the bond between O and H is weakened, so more H plus is going to be given. So you can say also that, okay, bond weakening, yeah. And then you say the easier to donate the H plus. So that is already the more than 3 points, okay, that is required for you to get the 3 marks over here. Yeah, so let's actually move on. Okay, so question number 8. Yeah, so we have total questions 9. So let's actually move on. Okay, so benzene, okay, C6H6 can be obtained from crude oil. Yeah, benzene reacts with Br2 in the presence of Br3. So this one is a halogen carrier. So forming bromobenzene as one product. Give the name of the formula of the other product that is going to be formed. So of course, okay, if you have benzene and you have the H is going to be substituted. So of course you have Br, so the H from here and another Br over there, they are going to join together. Okay, then they are going to give you HBr. So the name is going to be, give the name of formula. So I give the formula HBr. So if you want to give name, then hydrogen bromide. Yeah, hydrogen bromide. Now, in the presence of catalyst, bromine can be considered to be electrophile. So they already say Br plus is the electrophile. Complete the mechanism. So when you complete the mechanism, do check first. The bond is being formed at this carbon. Yeah, so you just draw from here to here. The movement of the electron, and they are going to have this and this. Show the H plus, because later you need to when you draw. This one is not complete. You put the plus over there. So the electron will come from here. Curly arrow must be shown. The two electrons will go in, and they are going to break the bond between the hydrogen. H plus will come out. And then you are going to get this Br over there. And then the circle, the ring will become complete again. Yeah. Now, name this mechanism. Quite simple. This is electrophile. This is electrophile. This is substitution. All benzene reactions, they are going to be electrophilic substitution reaction. We do have some other reaction, hydrogenation and so on. Oxidation and so on. But this one, whenever we are dealing with substitution into the ring, like for example, bromination, nitration, Friedel-Crafts, alkylation, acylation, all these are going to be electrophilic substitution. Now, benzene can be used as a starting material in the synthesis of this compound. You see, step number 1, suddenly you have C2CH3. So of course, you must actually have the halogenal alkane, C2, CH2, CH3, Cl, CH3, CH2, Cl. So same, but I'll use this. And then because we are dealing with the Friedel-Crafts alkylation, so it means you need to have halogen carrier, because you are substituting into the ring. Halogen carrier is required. And after that, doesn't matter what kind of alkyl groups that you have. When you use KMnO4 alkaline, then after that you go and heat, and then you put the acidify later. You are going to get benzoic acid. So not necessarily 2 carbon and then must have 2 carbon over here. No. As long you have alkyl compounds over there, they will give you a benzoic acid. And you see, from benzoic acid, from carboxylic acid suddenly become alcohol. There's only one way that you can do that. Carboxylic acid, you reduce. So in order to reduce carboxylic acid back into its primary alcohol, you need to use LiAlH4 in dry ether. So that is important. And here, the last part, you can see that the benzene ring, then suddenly no benzene ring. It means that it's like some sort of 3 double bonds has been substituted or do addition reaction. So this is going to be addition, electrophilic addition reaction. So this one, you are going to have, the reaction must happen with H2. The region is H2, and then you are going to use the catalyst, which is going to be platinum. So when they say suggest a suitable region, first you suggest CH3, CH2, Cl for step number 1, and then catalyst AlCl3. Depending on what you use. If you use CH3, CH2Br, then make sure you use the AlBr3. You can use last time they use FeCl3, but they have removed it, so let's actually stick to this. So you can use either AlCl3 or AlBr3. Now draw the structure of A. A is going to be benzoic acid, so you just draw. If they ask you, if they given you everything in skeletal form, it's okay, you can draw, but in this case it's not skeletal form, so you can just use represent them like this. So it's correct. Now identify suitable region for step number 3. So I already put LiAlH4 in dry ether. Done. So you just put in dry ether. They want region only, no need condition, but I just write also. And then platinum catalyst H2. Yeah, the region is going to be hydrogen gas with platinum catalyst. Yeah, so that is the step number 4. Yeah. Now the next question: deduce the number of peak. Yeah, of carbon 13 NMR. So carbon 13 NMR, you see, okay, this is going to be one peak because specific for this carbon. Okay, you can put this, okay, into symmetrical like this. You can fold, yeah. And then, okay, let me erase this first, then I'll just go through with you. So you see, you can put this, okay, symmetry over here. This is 1. This carbon is going to be carbon number 2, second environment. This and this can be folded, so it's going to be the third environment for the carbon. This and this is going to be different, okay, same, yeah, but different than 3. So it's going to be 4th, and this is going to be special, so it's going to be 5th. So there are total 5, yeah, 5 carbon environment. So I just put 5 over there. Number of peaks. Okay, let's move on. Question number 9. Okay, I believe the last question. Yeah. Now the proton NMR spectrum of compound E, yeah, is given in CdCl3. Okay. I think this question is they ask question directly. You know, why CdCl3 is used as a solvent? Yeah, this one we answered last time. Yeah. Why CdCl3 is used instead of CHCl3? Yeah, the reason, yeah, is going to be if you have hydrogen there, okay, there will be a peak. Yeah, there will be a peak. So in this case, if you use deuterium, yeah, deuterium over here, there is minimal peak. Yeah, but in our syllabus we say no peak. Okay, there is no peak if you use, okay, with CdCl3. So you can actually use that. Okay. Explain why tetramethylsilane TMS is added, yeah, to give you a small peak over here. Yeah, this one is going to be as a standard, okay, as a reference, okay, for, okay, measuring the chemical shift. Yeah, so it's a standard. So these two very straightforward questions. Yeah. Now, compound E is hydrolyzed, okay, by hot NaOH. Hot NaOH, okay, we have normally when you say hot NaOH, this is going to be hydrolyzed reaction. So normally we try to break the bond, okay, which is going to be the amide bond. Okay, or we try to break the ester bond over here. So here, okay, I don't see there is nitrogen here, so most likely this is going to be ester bond. Yeah, so O2. Yeah, so ester bond. So I know when they say they one of two organic product, one of it is ethanol. So of course, if it is ethanol, I automatically know the another product is going to be carboxylic acid. Yeah. So automatically name the functional group. Yeah, ester. So this ester, okay, the moment we know that is ester, yeah, it will give you a lot of information. Okay, what are the information that I will get? I know ester bond exists. Yeah, so I just put the ester, and I know that when I break this bond, okay, and I have ethanol. Yeah, they say one of the product is ethanol, so I just have to put C2H5 over there. Then only I get the ethanol. Okay, so I already found half of the compound already. Yeah, so I have 3 carbons here. Okay, I need here they say 9 carbons, so I have 6 carbons. And when I look over here, I see generally 1, 2, 3 peaks, yeah, of the hydrogen environment. So when I look closer, C2H5, CH3, CH3, then O, C, and then double bond O, then must be something else. Okay, and suddenly I know that, okay, this is going to be one hydrogen environment. Okay, same. And then I have this is going to be another hydrogen environment 2. So I must have another one more hydrogen environment, yeah, which is going to be the 5 over here. So if I go and keep on writing the carbon, then there will be more hydrogen environment. So the best thing that you can do is to put the benzene over there, C6H5. Okay, if you put C6H5 over there, okay, what happened? This, and this, they are all sharing the same hydrogen environment. Okay, so therefore, okay, you have one peak 2 peak, 3 peak, which is going to be possible to have that. Yeah, so this is going to be my, okay, the molecule that I'm looking at. Okay, so let's double check also. If I count this, C6H5, and then I have CO2, and then C2H5. Let's combine all of them together. C8, okay, hydrogen 10, okay, C8, another carbon, sorry, C9. C9, hydrogen 10, okay, oxygen, that's 2, okay. So C9H10O2, is that what they want? Yeah, that is what they want. Yeah, so most likely this is correct. Yeah, so describe the splitting pattern. Okay, they say 1.4. Let's see 1.4. Okay, 1.4. Okay, they have 3. Okay, most likely if you have 3 splitting pattern, okay, it means it's triplet. So it means the neighboring carbon have 3 hydrogen. So which one is the one that is going to be representing this? Okay, so the one that is most likely representing this, okay, sorry, the splitting is triplet. Splitting is triplet. The neighboring carbon atom has 2, yeah, because we talk about N plus 1, yeah. So 2 hydrogen. So I can see this is 3, it means 3 same environment. So you see, most likely they are going to represent for this hydrogen, okay. And the neighboring have 2, which is going to explain the triplet, okay. So that is going to be the answer, triplet. Okay, why there is splitting pattern? 2 hydrogen on the neighboring carbon atom. Okay, so that is going to be the reason. And then we are going to look at splitting pattern of 4.3. Yeah, so 4.3 is this one. Okay, so you can see that splitting is going to be quartet. Yeah, quartet. It means the neighboring must have 3. Yeah, 3 plus 1, then only you get 4 quartet. So most likely we are talking about this, yeah, this hydrogen. Okay, and then because they put 2, yeah, and then you see the neighboring carbon has 3 plus 1, yeah. So this is going to be, okay, quartet, okay, 3 hydrogen on the neighboring carbon atom. Yeah. Now, each molecule of compound E contains 5 protons, which give rise to peaks between 7 and 8.5. So here, each of them from here to here, okay, there are 5. So it means basically they're quite close, and then it is going to be 5. Yeah. So identify the functional group. Yeah. So identify the functional group. What functional group? The hydrogen. So they are attached to the aryl compound. Yeah, the benzene. So they are going to be attached to the aryl group. Yeah. So that. Yeah, attached to aryl group. And then they ask you give the structural formula of compound E. Yeah, because I know for certain now this is compound E and I want the structural formula. So structural formula, okay, you write down as, okay, CH3, okay, and then CH2, and then you have CO2, okay, CO2, and then you have C6H5. I think better to write it down as C6H5, the other way around. Yeah, you start from here, then CO2, okay, and then CH2, CH3. Yeah, this is going to be a better way to represent that. So I'll copy this and I put it there. Okay. So this is the answer. Okay. So if you look at the marking key also, okay, let me show you. C6H5. C6H5, CO2, C2H5. Yeah, so it's okay. Now, and then they say the mass spectrum, okay, includes fragments. Do remember the mass spectrum already changed into your A2, but do remember AS. So it's still 2 marks. They can still ask you, but I'm not predicting this to come out in your exam. I'm predicting the number of carbon, yeah, using the formula, yeah. How to find the number of carbon? That's going to be 100. Okay, divide by 1.1 times the abundance of N plus 1 divide by abundance of the N. Yeah. So so the one, please actually go through this. Okay. So make sure, okay, you can use this formula to find the number of carbon in that compound. Yeah, but here, okay, they say the fragment ion 29. So in order to do that, yeah, so you just easiest way is to write down there 12 and 3 is 15. Yeah, 12 plus 3. And then if you put this one, 12 plus 2 is 14. So oxygen and oxygen is 32, carbon is 12, C6H5 is going to be 6 times 12, okay, plus 5, which is 72 plus 5, 77. So if you look over here, you can, if you look at 29, so see which combination, this one and this one is 29. So these two, yeah, so C2H5 plus, done. And then make sure you put the plus, yeah. Then 77, you see straight away here, C6H5 plus, done, yeah. So that is going to be that part, okay. And the next part over here, question number 10, okay. They said identify which type of polymerization. So I can see carboxylic acid, alcohol, diol, and dicarboxylic acid. So condensation polymerization, yeah. Acyl chloride, diol chloride, yeah. And then the alcohol over here, the phenol, yeah. 2OH over there. So of course it's condensation polymerization. For this one, yeah, so you can rewrite this. If you rewrite CH3, CH, CF2, yeah, the carbon must have 4 bonds. So definitely must have double bond over there. And then if you look over here, the same, you try to rewrite over there, okay, CH3, CH, and then CH2. So must have double bond over here. The moment there is a presence of double bond, of course, they are going to go through addition polymerization. And the last one, okay, here, next one is going to be, they give you this, and then they say it can polymerize under suitable conditions. No other monomer is involved, so the same monomer within themselves. Okay, why? Because there is carboxylic acid and NH2. Yeah, so you arrange, okay, carboxylic acid over here, NH2 over here. Later I copied 3 because I want 3. So when you can remove the H and OH, so H and OH, and so on, you can actually show, okay, when I write down is nitrogen H, okay, then carbon H, CH3, C double bond O, and just to show, you just bring the H over here, H, CH3, C double bond O, just to show, bring the H over here, and then C, H, CH3, C double bond O, like this. Okay, they want 3 is done, and then they say clearly identify one repeat unit, okay, on your diagram. So repeat unit, yeah, so repeat unit. So the one that is repeating over here, of course, the NH and then up to CO, yeah. So I can draw here NH and CO. Okay, one repeating unit. Now, they say that it can also exist as 2 stereoisomers. Okay, so do remember, okay, if it is going to be 2 stereoisomer, okay, when I look at here also, I know, okay, what they're talking about, okay, because I know this is going to be a chiral center. Okay, carbon, there is hydrogen, there is COOH, there is CH3, there is NH2. Okay, so when you have 4 different groups and you want to actually show the stereoisomer, of course, we are talking about optical isomerism, but you need to be very careful when you show them. Yeah, carbon, you put the hydrogen over here. Okay, this one you put, okay, let's say hydrogen, so I put the CH3 over there. Okay, this one you show, okay, like this. Okay, maybe I show COOH, and then here you can actually show something like this going behind. Okay, that is going to be an H2. So when you draw, okay, the mirror image, okay, you can just, okay, put C, H, this one line, just follow the mirror. Yeah, just go here, then CH3. This one, if the mirror, if it is coming here, okay, to here, so of course this one have to come over here, and then you just put COOH, and then here, okay, NH2, you just put, NH2. Okay, so this is going to be, okay, the diagram, 3D diagram. Okay, and then the type of isomerism, optical isomerism. Now, for this question, yeah, they say that you put with hardener, yeah, no longer in your syllabus. I'm just going to ignore this. But okay, this one can quickly do. Yeah, the hardener is diamine. Diamine, they say alkyl chain with two amine groups which are not bonded to the same carbon atom. So you have different carbon atom. So NH2. So I just draw over here. Okay. If you want to skip this, also can. Yeah. So draw the structural formula. Okay, of a compound that will make a suitable hardener. I just need to follow this only. So if I want to draw a structural formula, then it's going to be NH2, okay, CH2, CH2, NH2. Yeah, this is, okay, you don't use this, okay. Structural formula means, okay, it must be like what I've done over here. Okay, with that, okay, we have done, completed, yeah. So I will stop recording. Okay, so I will also see how many of you still watching. Okay, 2, 3 still watching. Okay, so thank you for watching this. Yeah, so I have to go. Okay, so later I will compile the video and then I will upload the full paper. Yeah, so thank you guys. Bye.